Hey, good morning, everyone. We'll start in a minute or so.
Yeah, good morning, sir. Sanatan, I have a quick question.
Yeah,
Are you interested to work on any data science project if I directly get it from client in future? Is it possible?
like you're asking me, like whether I'm interested or not.
Uh,
Uh, it depends on the timeline, essentially.
oh,
So it would be like a freelance commitment, right?
yeah, yeah.
So maybe yes, maybe no. It depends on you can contact me definitely for sure. So see, my schedule is kind of it fluctuates quite a lot. So currently, I'm busy with so many additional commitments. So let's say if you talk about tomorrow, perhaps no, but maybe say after 3 weeks, 4 weeks, then I could actually check.
Yeah, sure.
Okay. So at that moment, I can confirm for sure.
Yeah, okay.
All right. Okay, I think there are two people right now. So let's wait for some more time and then we'll start. Now three. Okay. Let's wait for some time. Anyone with any questions? Meanwhile, related to clustering or anything that we have studied before.
So Sanatan, actually, like I'm riding two boats these days.
You're writing?
Two boats these days.
Okay.
So because like last month I got laid off, so like I'm searching for jobs and like I'm attending interviews also.
Mm-hmm.
So like yesterday evening something struck me. Like I'm just thinking like I just want to chuck the ERP field completely and maybe concentrate, maybe start applying on related to data science completely.
Okay.
So because like maybe it's a blessing in disguise that I've got the time now. Maybe this is the right time where I can really shift gears and shift the
Sure.
track.
Yes, you should rather. Yeah, we can start anytime. I mean, if you're interested, let's say if you need some sort of assistance, right? Maybe once you have applied to a company, maybe give me a message or send me a message or a text. That way, I'll be able to. I mean, if I know some acquaintances, right, or maybe say some relatives of mine or some friends,
Yes, yes.
okay, if they are working there, then I could kind of expedite the process. I cannot guarantee you a job, but I can definitely expedite the process.
Well, that's more than enough, Sanatan.
Yeah, I can definitely try it out. Okay. Given that I have some people whom I know, okay,
Yeah.
and I have see if I have friends in decent places, so maybe they know friends of friends. Okay, so I can definitely try.
See, like Sanatan, like I'm even okay with the role of a data analyst. Why? Because like, see, I want to start from the bottom of the pyramid so that I can like.
Sure, I mean we can do something about it.
Yeah.
I think Google will do it as well. Don't worry. Okay, in
Yeah.
case it doesn't pan out, right? Once you finish, I think you will have interview calls coming in soon, maybe next week onwards or 2 weeks from now.
Yeah.
So let's say if you can't, God forbid that doesn't happen, but let's say if you cannot make it up, okay, cannot make through like one of the companies, then definitely whichever company you are applying to, do reach out to me and say that, okay, this is the company, this is the application number and so on. And then I'll see what I can do.
Sure, Sanatan.
Okay. All right. Sure.
Thank you so much.
Yeah. All right. So let's start with the remaining topics of clustering. So just a quick recap, like just 5 minutes, maybe not even 5 minutes. So far we have seen a partitioning based algorithm. where you pre-specify the number of groups, the number of clusters, and this was called as k-means. Okay, and this algorithm cannot identify outliers. Okay, the vanilla version, by design, it cannot identify outliers. And we actually saw some techniques. So there are extensions to this that you can use to identify outliers. This can be used to determine, or you could say generate synthetic data also, that we saw in k-means smart. All right, so we have seen this before. We saw the limitations of this. So the limitations were that it cannot identify convex clusters. Please note that cannot identify outliers is not a limitation of this algorithm, because it is not there to determine outliers. It is there to do clustering. I'm just letting you know as a bullet point, by the nature of it, okay? It can, because it is not imbued in the design, right? So another limitation is that mean sometimes may not be a good representative. So we have k-medoids for this, like an extension for this. And for this also, because if it cannot identify convex clusters, then there are other algorithms that we'll see today. Okay. And also it's like highly susceptible to initialization. So you can reach to different, you can say solutions, different cluster memberships. And you can pick the one with the least within distance. Okay, so do many initializations. And pick the one with the least within distance. Okay, pick the one that converges to the least within distance. This is what we had discussed yesterday. So today we are going to see another algorithm. So I'll try to give you one algorithm from each basket that we talked about yesterday. So this algorithm is called as density, or let me call it dbScan for now. The full form is density-based spatial clustering of applications. So this is DB, okay? Spatial clustering of applications with noise. Okay, so dbScan. All right. So the name itself suggests that, okay, it can identify outliers. Okay, in the name itself, it says, okay, it can identify noise. So can identify outliers. So it is there in the design of this algorithm. Okay, it is density based. And the third thing that you want to know is that you don't need to pre-specify k. It can automatically figure out the number of clusters. Okay. So these are the things that we need to know about this algorithm. Let's see how it works. So I'm doing a two-dimensional visualization, so it's easy to understand. Okay. Okay, let's say this is the data that we are having. Okay, this is the data that we are having. So the idea is what this algorithm will do, it will try to identify two types of points. It will try to identify two types of points. One is called as a core point. Okay, one is called as a core point, and the other one is called as a boundary point. So the points which are not core points, they are called as boundary points. Now, what is this core point? So with this algorithm, so far there are no hyperparameters, right? If you read the definition of it, but intrinsically there are two hyperparameters, which are the following. One is called as EPS or the radius. EPS stands for epsilon, a small radius essentially. Okay, let's say this value is say 0.5. Okay, what it means is, okay, you take a point, you take any point wherever you want. Okay, so I'm showing you how this algorithm starts. So you take any point, okay, and draw a circle around it of radius, whatever the EPS that we specify. Okay, so let's say the radius is around 0.5. And we draw a circle around it. Okay, so this is 0.5. This is EPS. Okay. So you see that 2 points got encapsulated in it, right? Okay. So you will call this point to be a core point if it has more than min points. This is also called as min samples in the radius, okay, in the direct radius. Okay, let's say this number is 5. So what you are going to do is you are going to draw a circle around a point, including the point itself. Okay, do you think you have 5 points for this? In the circle that you have drawn, how many points are encapsulated, including the point itself?
3.
3, right? So is it a core point? Does it have more than min samples?
No.
No, right? So this is not a core point. You can say it's a boundary point. Okay, this is a boundary point. Now, let's say if I would have drawn a circle around this point. Okay. My drawing is bad, but I hope you get the intuition. Do you see that there are 5 points, including itself? Okay, including itself. The point should be included. So can I say this is a core point?
Yeah.
This is a core point. Okay. Now let's try to understand what this algorithm does. I'm going to give you the simple explanation for this. By the way, you can go deeper, and if you want to study more the intricate concepts, how it works, that's all not necessary. Okay, nobody will go that far. But the idea is this. Do you see that there are some core points and there are some boundary points? Let's focus on the upper part. Like if I draw a circle around each and every point, do you see that there are some core points and then there are some boundary points?
Yes.
Okay, so maybe let's say if this was like this, okay, maybe let's say like here. So this is also a core point, right? Maybe say this point. Yes, sir. Okay.
Yep.
So the idea is these boundary points are responsible for connecting these core points. Yes or no? Can I say that these boundary points are responsible for connecting the dense regions? And dense regions are those where there are a lot of core points. This is also a core point, right? If you focus carefully. Okay. Maybe this will also turn out to be a core point if you carefully see. Okay. So what this algorithm is doing, in simple words, it keeps on drawing circles. Okay, it keeps on drawing circles. So if you started your algorithm from this point, okay, this first point, which came out to be boundary, you saw 2 new points being encapsulated, right? So what you do is, if this point got encapsulated, you draw a circle around this point also. You draw a circle around this point also. And if you keep on doing it, do you agree with me that all of this would be encapsulated in maybe say excluding this point, all of this would be encapsulated?
Yes.
Okay, I mean, if you keep on drawing circles, okay, some of them being core and some of them being boundary, does that make sense? Yes or no?
Yes. Yes.
Okay, so you will call this.
So
yes.
based on the nearest points, the algorithm will automatically found that there is a boundary point or a core point, right? Like
Yes, this is the definition of a point. Okay, so think of it like this. You start with any point. Okay. Forget about core and boundary. You draw a circle around it. Either it would be a core or boundary, right?
Yeah.
Some points will be encapsulated. If no points are encapsulated, do you think this will belong to any group?
No.
No, right? Okay.
Yeah.
But let's say if some points got encapsulated, can you take those points and keep on drawing these circles sequentially?
Yes.
So you will hit a region beyond which no other points will be, after a while, no other points will be encapsulated, right? So you'll be stopping this process. So can I say that this process will stop when all these points are kind of encapsulated,
True.
right? So some of these are core and some of them are boundary. In simple words, I'm saying that within these points, okay, within these points, there are some core and some boundary, right? Okay. So if the number of points, okay, if the number of points are greater than, okay, are greater than the min samples that you saw, then you can call it as cluster 0. Okay, then all these points will be given the label as 0. Okay. Now let's say you start with this point. Okay, there are some points remaining which have not been clustered, right? So repeat the same process that you did earlier. Choose any point that you want. So if I choose any of these points, okay, if I repeat the process, do you agree that this will all belong to the same cluster?
Yes.
Okay, I mean, if you keep on doing this, this will all fall into the same cluster. Okay. So is it visible that, okay, we have more than min samples here? More than 5 points in this group, right? If you keep on drawing circles on and so on and so forth. Okay. So this you can call it as cluster 1. Okay. So all these points will be labeled as 1. Okay. Now what about these points? Let's say you start your journey here. So only 3 points would come.
Yes.
Is it more than 5? No, right?
No.
And is there any core point here? No, right?
No.
So all these 3 points, they will not be classified as a cluster. They will all be outliers. And outliers are typically denoted with -1s. Okay. And what about this point? Also an outlier? Yes or no? Because you have to complete this process for every point. If you could have reached this point from this, then it would be included in the same, right?
Yes.
Okay. So you can see that, okay, this is not included. So it is called as an outlier, and there is no other point to reach. So that's why it's an outlier. Okay. So this is where the process stops when you have visited every point once. All right. This is a very simple algorithm. Now, what's the usage of core and boundary? Okay. So see, if you think about core points, they belong to dense regions, right? Because core itself is like a cluster, right? Yes or no? Yeah. See, what is the definition of a group? It should have more than min samples, right? And what is the definition of a core? It's the same, right?
Yes.
It should have, in the direct vicinity of the circle, it should have more than, including itself. Okay, it should have more than min samples. So can I say a core point always belong to a cluster?
Yes.
Okay, it will be definitely a part of a group, right? So you can say that these core points are nothing but some essential celebrities or important people, influential personalities. Right? If you think from a network perspective, which people do you think will have a very dense connectivity? Popular people, right?
Yeah.
So this algorithm is very, very frequently used in those domains where you want to identify influential people. Okay. So core points are those, but boundary points are those like us regular people. Okay. Let's say I'm not very popular, or we all are not very popular. Maybe you are in your respective community, but let's say from a generic standpoint, okay, we are not politicians, right? We are not actors, we are not celebrities. Okay, maybe one of you is the CEO, so you may be a core point with respect to your community, with respect to your industry, but definitely not me. Okay, so I am a boundary point right now. So the idea is these boundary points are kind of responsible for connecting different companies or different communities, different dense regions, if you see carefully. Okay. And boundary points also can be forming a cluster, even though they don't have a core point. Because if you keep on, so assume that this is the scenario. Assume that this is the scenario. Okay. So all of these points will be boundary, right? Let's say if you take this, okay. None of them have the min samples, but when you combine them as a group, you do have more than n samples, right? So it's a chain-like structure that you are forming. And it's a group, and none of the points are essentially core points. Okay, so you can say it's a group, but none of them are core. All right. So there is no essential, yes.
Example that you have driven, Sanatan, like there is a like a line of points here there, and there is more than a minimum samples, right? So why don't it be?
No, it's a group only. It's a group only. I'm not saying that none of the points is a core point, right? This one that I drew.
Yeah.
If you draw a circle around any of these points, let's say this point, you'll get this, right? So how many are there in the vicinity? 2 only, right? Direct vicinity.
Yes, yes.
So it's not a core point, right? Definition of a core is if it is directly surrounded by more than n samples. Okay. But if you keep on drawing around this point, you'll capture these points, right?
Yeah.
Maybe you'll capture these points, you'll capture these points. I hope you get the intuition, right? So all of them would be covered, but none of them are core points essentially, right? Yes or no? If you look at the total number, it is greater than n samples. So it's a group, but none of them is a core point. Okay, none of them is a core point. Okay. So this is DBScan, very effective algorithm. So just a few quick questions about this. I mean, you can use these core points to find influential people or important points. Okay. Boundary points are essentially those points which kind of keep the data connected, keep dense regions connected, if you think about it. Okay. There is one more thing. If somebody asks, what is the shape of the clusters that this can determine? So it can easily work with these shapes also. Yes or no? It can easily work with these shapes also. See, if I keep my epsilon to be fairly small, can I say that these points will all belong to the same cluster? Even if you draw a circle around this point, it is not going to touch the other one, right? Does that make sense or not?
Yeah.
Okay. So if the radius is fairly small, it can easily work with these non-convex clusters. Okay. So it can identify non-convex clusters. So these two will be two different clusters. And the shapes are essentially chain-like. Okay. So it forms chain-like structures. Okay, so this is your DBScan, can identify outliers. So you can easily remove those outliers. But please note that there is no ground truth. You need to be the domain expert to make a call about it. Okay, and okay, one more thing. What if I decrease, okay, what if I increase min samples? What can you say about the number of cluster? What can you say about the number of outliers? Let's say previously it was 5 and now I make it 10. What do you think? The outliers will increase or decrease?
Outliers, right.
So increasing min samples will lead to increase in outliers or decrease in outliers. Okay, think about this region. Okay, so do you think any point with EPSS 0.5 will be a core now in this C1? Min sample is 10 now.
9. No.
No, right? And will any point be a part of a cluster? How many points are there if you carefully see?
9.
9, right? So will there be a cluster? No, right?
Yeah.
You need at least 10 points. So there will all be outliers. So can I say that in general, if I increase the number of min samples, okay?
Increase. Yeah.
Okay, the number of outliers will increase as well. And which value of the radius increases outliers? Small values? I mean, decreasing the radius will increase outliers or increasing the radius will increase outliers?
Decreasing the radius.
Decreasing the radius. Okay, so keep these two things, as you can say, key takeaways. So this is your DBScan. Let's do one more, which is hierarchy based. So this is called as agglomerative clustering. Any questions about DBSCAN though? Before we start the next one. Is this clear?
Yes.
So this is the next one, agglomerative clustering. It's a hierarchical algorithm. It's a hierarchy-based algorithm. Will give you a structure like a decision tree. Okay, very similar to a decision tree. Okay, you have to pre-specify the clusters. And it has its own hyperparameters. I'll talk about it in a bit. It has its own hyperparameters. We will speak about it in a bit. Yeah. So let's see a simple illustration of how this algorithm works. It's very simple, by the way. So imagine these are the two dimensions. I have some points, and maybe the points are like this. So this is x1, this is say x2, this is x3, this is x4, okay. Maybe so this is x5, okay, say this is x6. Okay, let's say these are the 6 points that I am given. So what we have to do is we have to build a structure. Okay, so I'm going to show you a visualization. So imagine currently every point is a cluster. So how many clusters do I have?
5. Sorry,
6, right?
Yeah.
6 clusters. Okay. So let's say this is x1. Please note that the distance between these points does not illustrate anything. As of now, the structure that I'm drawing, this structure is not based on the distance. This is just to demonstrate. So every point is a cluster in itself right now. So to identify bigger groups, what do? We merge, right? So what you are going to do is you are going to merge 2 groups at a time. Okay. So which 2 groups do you think should be merged? Which 2 groups have the distance, least distance? So on the y-axis, think about it, that there is this distance. Okay. So on the y-axis, there is this distance. So the height will demonstrate the distance. So which 2 points are the most similar? What do you see? Are the closest?
X1 and X4.
So you merge x1 and x4.
X3.
And let's say the distance between them is say 0.5. So this would be 0.5. Does this make sense? So if the distance between them is 0.5, so do you realize this? I can merge it like this.
Yeah.
Okay. All right. A few other things. If multiple points are at the same distance, you will merge them in the same. You can say step.
Okay.
There might be other points also, right, which are at the same distance. Maybe say there was this x7 also at the same distance. So you would merge x5 and x7 as well to the same step at the same distance. Okay. So essentially what you're doing is you are finding the least distance, the least pairwise distance, and then merging it. Does that make sense?
Yes.
Okay, great. Now, at this point, how many clusters are remaining? So you have merged 2 clusters into 1. So 5.
Yeah.
So if somebody asks what are the clusters, so you will say x1, x4 is 1, x2 is another, x3 is another, x5 and x6. Okay. So these are the 5 clusters remaining. Now, which 2 clusters do you think shall be merged next?
X2 and X3.
X2 and x3. So let's say the distance is 1. Okay. This distance is 1. So one of the hyperparameters that you think of is a distance metric, right? How to compute the distance? You can use Euclidean Manhattan. We have studied many metrics, right? So the distance metric is something that you can use as a hyperparameter. Okay. So the next step would be to merge your x2 and x3. So this is x2, this is x3. This is say x2, x3. Okay, at this moment I have 4 clusters remaining. Any other at the next step, what do you think?
again going for another step.
I mean, it could be x2, x3 with x6, right?
Yes.
Okay, looks like this. So now there comes a catch. Okay, now there comes a catch. It seems like this, right? X2, x3, and x6 should be merged. Yes or no?
Yes.
Okay, it seems like it. Okay, but there is a catch, and the catch is this. Okay, the catch is this. Let's discuss this catch. There's a caveat here. Okay, so I'm going to again show you an illustration, and then we will talk about it. Okay, so the catch is, see, I know how to compute the distance. Okay, I know how to compute the distance using Euclidean Manhattan, some formula. But the point is, if there are multiple points in a cluster, let's say this is cluster 0. Okay, maybe say this is cluster 1, and say this is cluster 2. Okay. I want to figure out which two clusters should be merged next. That's the objective. Okay. So how do I decide which two clusters should be merged? So typically I say that the one with the least distance shall be merged, right? But now there are multiple points within a cluster. So with respect to what point I should take the distance? Do you realize that, the bottleneck here? See, if there is just 1 point and 1 point, I know the difference should be taken between them, right? And I know how to compute the distance between two single values. Now, if you want to compute the distance between C0 and C1, there are 6 possible ways to measure the distance. Yes or no? You can compute the distance with respect to this and this. You can compute the distance with respect to this and this. So for one, you can say sample in C0, there are 2 possibilities in C1, right? And in total, we have 6 possibilities. So which possibility shall we pick? Right? There is, you can think of distance between their centroids. Yes or no? So there are many ways to look at it, right? So let's define the second hyperparameter that I spoke about, that I didn't speak about, but I mentioned that, okay, there are hyperparameters which we will see now. Okay. So one of the hyperparameters is linkage. So linkage defines the representative points. Okay. Linkage will tell you what are the points that represent a cluster. Okay. So one simple idea is to compute the distance between C0 and C1. I can choose the closest points, right? Yes or no? I can choose the closest points.
Yeah.
This is called as single linkage. Choosing the closest points. Okay. So for C1 and C2, it would be this. And for maybe say, sorry, for C0 and C2, it would be this. Does that make sense? Now, which are the closest? C0, C1, C1, C2, or C0, C2?
C0 and C1.
So they will be merged in the next step. Does that make sense? So they will be merged in the next step.
2 clusters will be merged.
Yeah, at every step, what do you think? What is happening?
Okay.
You're merging 2 clusters, right? So I'm just giving you an analogy here. Okay, how do you see distance computation is okay because I know the formula. But with respect to what I should compute the distance, that is what we are trying to figure out. Okay, so if there are 3 possibilities that I have to merge, okay, so I can combine C0 and C1, I can combine C1 and C2, and I can combine C0 and C2. So what should I merge first? The one with the least single distance.
Yes.
Does that make sense? Okay. Similarly, there are actually many different linkages. Let's talk about complete. So complete is use the furthest points or farthest points, whatever you want to call it. So if you want to define the distance between, say, C0 and C1, you'll be using the distance maybe this. Does this make sense? This would be the distance between C0 and C1. Okay. And perhaps this would be the distance between C1 and C2. And I think this would be the biggest distance between C0 and C2. Yes or no?
Yes.
Or do you think this is bigger? I think this is slightly bigger. Okay, but anyways, you get the point, right? So choose the furthest set of points, okay, to compute the distance. Now, which one looks, so let's say this is 20, this is 22, and this is say 23. So which one shall we merge?
20 for sure. C.
20 for sure, right? So you are again looking at the minimum amongst the furthest distances. Okay. Let's think of centroid linkage. So take a distance between the centroids and then make a decision. Okay. There is something called as average. Average is a little different than centroid. Okay. Don't get confused between the two. So if I'm trying to combine C0 and C1, how many pairs are there? Yes, go on. Somebody was asking something. Any questions? See, centroid distance is the distance between the centroids. So this would be the centroid for these 2 points. This would be the centroid for this. So this is the distance between your C0 and C1. Okay. Similarly, distance between C0 and C2 would be this. And distance between C2 and C1 would be this. Okay. And then you pick the minimum one. This is centroid. Average is a little different. Okay. Both are not the same. So what is average? Let me just describe. So let's say you were trying to merge C0 and C1. Just assume for now that you were trying to merge C0 and C1. How many distances are possible between C0 and C1?
What's your question, Sam?
How many distances are possible between C0 and C1? If you're looking at the across distance between C0 and C1. In how many ways can you measure the distance between C0 and C1? There are 3 points in C0, 2 points in C1. So what are the total ways possible?
6.
6, right? Can you add all those 6 distances and divide by 6? We can do that, right?
Yeah, we can do that.
That is the average linkage. Okay, so it's the average of all the 6 distances. Okay, so similarly for C0 and C2, what is the total number possible? 12, 3 into 4.
Yes.
So compute all the 12 distances, add them up, and divide by 12. That will be the average distance between C0 and C2. Same thing you do it between C1 and C2. Whichever is the least average distance, merge those two. Okay.
Okay.
It's not the same as centroid. Okay. Please keep that in mind.
Yeah.
Okay. It's slightly different. Okay. Then there is one more, which is actually quite popular. This is called as Ward's linkage. He was a person who proposed this.
We're only looking at 1 point, and then the average we are looking at the all points in the cluster. So that
Yes. So with respect to the centroid, and average is with respect to all points. Okay, with respect to all points across. Okay, let me call it with respect to all pairwise distances. Okay. So let's see what is Ward's linkage. Okay. So Ward's linkage is it is inclined more towards the definition of clustering. So when you want to merge 2 clusters, should they be compact or should they be dispersed? Like more dispersed? Like upon merging, the clusters should have more compactness or they should be like more dispersed.
more compactness.
More compact, right? Okay. So think of this. Maybe I'll show you in a single, 2 dimensions is also fine. So let's say this is the scenario. This is C0, this is C1, and maybe say this is C2. Okay. So let's assume that you are merging C0 and C2. Let's assume that you are merging C0 and C2. How do we measure compactness or let's say separation? How do we measure compactness or separation? Okay, maybe in 2 dimensions it's not clear, but say in 1 dimension. Let's say you have these 2 points in a cluster right now. Okay, and this is another. You will try to merge these points. Okay, let's say this is 1, this is 2, and this is 4. Okay, or maybe say this is 5. My question is this: if you want to merge them and then see how much would be the compactness, how would you measure it? How do you measure it?
You're asking how do you measure the compactness between?
Yeah, how do you measure the spread of the points? In one dimension, it is quite straightforward, by the way. We have done this in decision trees also.
So if we were merged this into one cluster, then we'll find the distance between the points, and then
One way to do that is like if you take all these three samples, right? I can look at the pairwise, all pairwise combinations and sum them up.
yes.
Another way is to measure the variance, which is the same thing, if you remember. We discussed about this in decision trees also. See, one is that you take all possible pairs, 1, 5, 1, 2, and 2, 5, and you compute some distance on it, and then sum it. Do you think it will tell me how much the spread is? It will, right?
Yes, yes.
So D could be Euclidean, D could be square, D could be Manhattan. If you use square distance, this is equivalent to computing the variance, n square times the variance. Okay, so what Watt's distance says is this. Okay, assume that you would have merged C0 and C2. Okay, so you do it in each dimension. So currently you are doing it in one dimension. You do it in each dimension. So there are two dimensions right now, right? This is x1 and this is x2. So first you find the variance across x1, then you find the variance across x2, and then see how much is the variance across the dimension and sum them up. So that is the total variance across the two dimensions after merging C0 and C2. Similarly, you try to see what is the variance for C1 and C2 and what is the variance for C0 and C1. Which ones would you merge? The ones with the least variance or ones with the most variance?
Least.
Least variance. That is Watt's linkage. So Watt's linkage, what it does is it minimizes the compactness, or you can say, sorry, maximizes the compactness, minimizes the variance between the clusters. Okay, so it focuses on compactness. And this is actually chosen to be the best, like one of the best metrics, one of the best linkages across all of them, if you want to do good clustering. Okay, now the idea is this: if I keep on doing this, what would happen at the end? I would just have one cluster remaining.
Yeah.
And all the points will be there in hit. So if you want, say, 3 clusters, where would you stop? You would stop at this point. If you wanted 3 clusters, if you say that k is equal to 3, see, this algorithm will ask you what is the value of k. Okay, you will have to specify it, just like k means. So if you say that k is equal to 3, which will be the 3 clusters? So one would be x2, x3, and x6. This would be one. One would be this x1 and x4, and the other one would be x5. Does that make sense? So maybe you give x5 the label as 0, x2, x4 the label as 1, and these would be given the label as 2. And there are 3 clusters, right? 0, 1, and 2. The cluster labels will go up to k minus 1, right? Is this clear? Any questions? If it is not clear, ask again. Shall I repeat this?
No, sir, it's clear.
Yeah. Okay. Great. So this figure has a special name. It looks like a decision tree, right? Here, if you look at it from top to bottom, can I say that it will appear like I am dividing the samples?
Yes.
Okay, so this is called as divisive clustering. If you look at it from bottom to top, can I say that I am aggregating the samples into clusters? This is called as agglomerative clustering. Which do you think is easier to understand? Divisive or agglomerative?
Agglomerative will be easy to
Easier, right? Okay, which do you think would be more expensive? Divisive or agglomerative? Or do you think they both are the same?
I think expensive.
Divisive would be super expensive. Okay, think about this. Let's say you're looking at it from top down. How many partitions would you want to find? So initially there are 1. what would be the next step? 2, right?
Yes.
So you'll be doing it in 2 partitions. Now, how many combinations are possible in 2 partitions? Think about it. See, maybe you can keep 1 in one and 5 in other. Yes or no?
Yes.
You will have to check, right? You cannot make a judgment without that. So if you keep 1 in one and 5 in other, what is the total number of combinations? Think. You keep 1 in one and the remaining 5 in other. 6 combinations, right? There are 6 samples. You keep x1 in one and the remaining in other.
Okay, okay.
You keep x2 in one and the remaining in other. 6 combinations, right?
Yes.
Now, it is also possible that you keep 2 in one and 4 in the other.
Yes.
So that is 6 choose 2. Okay. Now you think of keeping 3 in one and the remaining 3 in other. So that is 6 choose 3. So the total number of combinations that you have to check is 6 choose 1 plus 6 choose 2 plus 6 choose 3. Yes or no?
Yes.
Now, I want you to think about this. How many combinations you have to check? Just 6 choose 2. If you are starting from the bottom.
In agglomerator. Okay.
It will be 6 choose 2, right? But in the top case, it was 6 choose 1 plus 6 choose 2 plus 6 choose 3. That is much, much more. Okay, so that is why agglomerator is preferred. You can do the other way around. Okay. So, for bigger samples, right, Divisive becomes even more expensive. This is just a 6 sample data set. Okay, so wherever you see, you will always have the implementation for agglomerator. Divisive will not be shown to you. Okay, you will not see any implementation of Divisive anywhere. You will only see implementation of agglomerator. Okay, but I just wanted to let you know, okay, the other name for this is Divisive if you look at it from top to down. Okay, so this is called as.
Sandon,
Yes.
can you please give me a brief 2-line about the word linkage still?
So what's linkages? So merge those 2 clusters, which are the most compact, which will give you the most compact result. Okay, see it in 1 dimension. Okay, see it in 1 dimension. Okay, let's say there are these 3 clusters. Okay, let's say this is 1, this is 2, this is 5, this is C0, this is C1, and maybe say this is say 10 and 11. Okay, and maybe say 12 is also there. So how many possibilities are there for you to merge? C0, C1, C1, C2, and C0, C2, right?
Yes.
3 possibilities, 3 pairs I can make. Which one should I actually merge?
The nearest C01, yeah.
Why? Because don't you see that the resultant clusters are compact? In 1 dimension, does it feel like if you would have merged C0 and C1? Let's say if you would have merged C0 and C2, do you see that the spread is much, much more? It's a very widespread cluster.
Yes.
So that's not the definition of clustering, right? Clusters should be compact.
Compact, yeah.
Okay, and think about the other way around where you are merging C1 and C2. Okay, it's still a widespread cluster, right? The variance is much more. The
Yes.
compactness is much high. Okay, it should be, compactness is much lower as compared to C0 and C1. Okay, so C0 and C1 should be merged. In 1 dimension, it is quite easy to interpret. In 2 dimension, you think of it as I will merge those 2 groups, which will give me the tightest clustering.
Okay.
All right. So this is your agglomerative. I think I forgot to mention one thing. So this figure is called as a dendrogram. The name of this figure is a dendrogram. Okay, I'll show you the implementation that how to plot a dendrogram, okay, and how to make inferences from it. Okay. This figure is called as a dendrogram, this hierarchical figure. Okay. It's a tree-like structure, right? Like decision trees, but has a special name. Okay. Now let's see. So let's see some evaluation metrics. How to evaluate the goodness of clustering algorithms. So one fundamental difference that we have already discussed yesterday is this, that there is no ground truth. It is unsupervised learning. So I cannot really compare, okay, because there is no actual values. I cannot compare my predictions, my output with the actual values because actual doesn't exist. It's unsupervised learning. I do not know what the true clusters are. I don't know that. But the only thing that I know is the within distance that I am frequently using, how tight the clusters are. Okay. So I only know of those things. So when you're talking about evaluation metrics for clustering algorithms, what we would do is we will only evaluate, you can say in some form. Okay. Most of these evaluation metrics will try to use the concept of within distance and across distance. Okay, in some way. Okay, I'm saying it will be the combination of and or in some way. Okay, whatever evaluation metrics that you will see. Okay, so let's start with some of them. Maybe I'll try to cover 3 or 4. So let's start with the first one. Okay, let's go by the easiest one. Okay, let's start with something called as silhouette samples. Okay, let's see what it is. Okay, so I'll give you a small illustration and how to compute this as well. So imagine this is the clustering that you get. This is C0, this is C1, maybe say this is C2. Okay, and you can have more clusters. This is just for visualization sake. Okay, so I want to evaluate how good the clustering is this. Okay, so what silhouette samples does, it computes a score for every sample. Okay, it computes the goodness score for every sample. You can call it the goodness, compute the clustering goodness for every sample. So the idea is for each sample, it will try to give you a value. Okay, and we will discuss, okay, if this value is higher the better or lower the better in just a minute. So let's say I have to compute for this sample. Okay, so this is some sample xi, and I want to compute how good this has been clustered. Okay, you can do it for every sample, by the way. So let's see this. So silhouette sample, let's call it SS. Okay, for sample xi is given as, okay, let's take this value. So you are going to compute it with respect to the nearest cluster. So compute it with respect to the nearest cluster. So which is the nearest cluster to xi? Okay, xi belongs to which cluster?
C0, C0.
And what is our next nearest cluster to it?
C1.
C1. Okay, keep this in mind. Okay, all right. So you are going to compute this with respect to the nearest cluster only. Okay, you're not going to include C2. So what do you want? The separation between this xi and C1 should be high or low?
Low separation.
No separation. How far apart they are? These are clusters, right? They are different clusters. Xi belongs to C0 and C1 is another cluster. What do we want? We want more distance between the clusters, or we want less distance between the clusters? We want more distance between the clusters, right? By definition of clustering, clusters should be far apart. Each cluster should be compact, but clusters should be far apart, right? So even the nearest cluster should be far apart. Yes or no?
Yes.
If it was nearby, then they would be in the same cluster, right? Okay. So if it was a good clustering, C1 points would also be in C0, but that's not the case, right? So the clustering that you're obtaining, you are saying that, okay, the nearest cluster should be far apart. Okay. So the idea is this, let's compute the average across distance. You're doing it with respect to a sample. Okay. So if you're computing the average across distance, okay, let's call this distance as B. With respect to xi, the nearest cluster is C1. So how many distances will you compute with respect to xi from C1? How many distances will we compute? 5, right? See, the definition is across distance. Okay, across means you are doing the distance between two different clusters. Since we are doing it for sample xi, the next nearest is C1. So how many samples in C1 are there? 5. So you will be computing 5 distances. Does it make sense?
Yes.
So can you take the average of all those? You can, right?
Yeah.
That would be B. Okay. Do you want it to be high or low?
Across distance.
High.
High.
It should be as high as possible. Okay. Subtract it from average within distance. Let's call this distance as A. Okay. So you are in cluster C0. So how many distances will you compute for this xi within the cluster? These 4, right?
Yeah.
So can you compute these 4 distances, take the average? So what would you want? Compact or, I mean, distance should be high or low? It's within distance.
Within distance should be low.
Low. And divide this by, so see, if you look at the numerator, right? Numerator can be any value between minus infinity to infinity. Okay. So to normalize this, I'm going to divide it by the maximum of A and B. Okay. Let's try to understand what is the maximum value that I can get for this. Okay. Now think of this. What is the most ideal scenario? Okay. The most ideal scenario is this is your point xi. Okay. Okay, this is your point xi. Okay, for which you want to compute. It belongs to some C0. Okay, it belongs to some C0. The next nearest cluster is, let's say, very, very far away. Yes or no? Does that make sense? Is the most far away, right? That is what I would prefer as to be the best clustering, right? Does that make sense or not?
Yes.
So what can you say about this B? B should be how much in the best case? As high as possible. What is the highest value possible? Infinite.
Yeah.
Okay, so let's say this is infinity. And what is the least value possible for average within distance? It could be a single sample, or it could be that there are other samples which are lying on top of it. What would be the average within distance in that case? 0. Distance is always positive, right? It cannot be negative. Okay. So in the best case, it can be a single sample, or there can be other samples which are lying on top of it, whose within distance is 0. So B is infinity, this is 0. So infinity minus 0 divided by maximum of 0 and infinity, which is infinity. So what would this value be? 1. Okay. So in the ideal case, the highest value is 1. Does this make sense? This is the highest clustering, right? Highest clustering score. The best clustering that I would want. Okay, let's see this. The worst case, which I am going to say it will not be possible, but the worst is the worst, right? Maybe someone can come up with this algorithm and the result will demonstrate that, okay, that can happen. Okay, so this is the best case, if you think about it. So the best case is like when within is 0, okay, and this across is high. Okay, it can be any number. Okay, across is high. It can be any number. So in that case, silhouette score will turn out to be, silhouette sample will turn out to be 1. Okay. I just mentioned. Sorry. Yeah, this is fine. Okay, let's see the worst case. So this is your xi. Okay, this is your xi. It's a big, it belongs to this cluster C0. Okay, there are other samples in it. Okay, what do you think would be the worst case? Think about it.
The within distance is always very
high.
high. Yeah.
Okay, and what is the across distance? Very less.
Yes.
And what would be the least value for any distance? 0, right?
Yeah.
Okay. So I'm going to give you the worst case, and the worst case is this. There is another point. So this is your xi, right? Assume that there is another point xj, which is having the same coordinates as xi, but this belongs to cluster C1. Is it possible, by the way, first of all?
No.
Not possible, right? But can I say this would be the worst case if ever that happens? Yes or no? 2 points which are exactly the same, but they lie in a different clustering, different cluster. That would be the worst case, right?
Yes.
Okay. So let's try to do your silhouette score for this xj, just to understand this. Okay. Just to understand this. Okay. Assume that xj is the only point, or there might be other points on top of xj which also belong to this cluster 1.
The cluster 1. Okay.
Okay. So what can you say about their within distance? Let's talk about across distance. Okay. See, the formula is this. Okay, just a second. Okay, just give me a second. Okay, I'll have to give it a thought. Do it for xi only. Okay, do it for xi only. Okay, let's say we are doing it for this xi only. So what is the across distance? So there is another point xj, which is in a different cluster.
Yes.
So what, and it lies on top of it. So what is the across distance? What is b? It will be 0, right? In the worst case. Yes or no? See, how do I compute this average across distance with respect to the next nearest cluster? I am saying you belong to a certain cluster. Let's say you belong to this red cluster. Okay. There is another point which is on top of you, which also has the same coordinates. Okay. But this belongs to purple cluster. Okay. There can be more points here. Okay. Which are the same coordinates, but they all belong to purple cluster. Okay. So what can you say about the red point? What is the average within average across distance? 0, right?
0.
Okay. Now, what is the within distance? Within distance would be high, right? Because there are so many points in this.
Into 1.
Not 1. Within distance would be high, right? I mean, some value can be infinity as well if there are more points. Yes or no? If you look at the average within distance, the A value, it would be high, right? For a bad clustering.
Yes.
Okay, it would be a bad clustering. Okay. So let's put it in the formula just to understand this. So what was the value B? 0.
0.
This was any value A, which is a high value. So this is 0 minus A divided by max of 0 and A. What will this come out to be? 0 minus A divided by max of 0 comma A.
Minus 0. Sorry, minus.
Minus 1. What is max of 0 comma A? A, right? A is a positive value. A is a distance. Okay, so this will come out as minus 1. So in the worst case, this is minus 1. All right. This is just to illustrate this. So silhouette score, okay, is silhouette sample is between -1 to 1. So can you compute it for every sample? We can compute it for every sample, right? For a given data set. Yes or no? If I tell you the data set and I give you the cluster labels, can we compute it for every sample? We can, right?
Yeah.
And then you compute the average of the silhouette samples. So I'm saying you now compute the average of the silhouette samples. So for each sample, you compute this and then you do it. So if there are n samples, you compute the n silhouette samples and then compute the average of it. Can I say this would be the overall clustering score? Overall silhouette sample score? Yes or no?
Yes.
Okay, this is also called as silhouette score or silhouette coefficient. What do you want, higher or lower? The value is, see again, the range, if every value is between -1 to 1, and you take the average of it, the average will also be between -1 to 1, right? So the highest value is still -1 to 1, Okay, so 1 is in the ideal case, -1 is in the worst case. Okay, so you want it to be closer to 1. Okay, you want it to be closer to 1. Okay. All right. This overall silhouette score is also called as overall silhouette sample is also called as silhouette score and silhouette coefficient. Okay. All right. Let's do some more. By the way, this is the most preferred one. This the one that we are discussing is the most preferred one. Okay. Let me see if there are any messages in the chat window. Okay, none here. Okay. So next, what we are doing is something called as a Davies Boolean index. Okay. So imagine this is a scenario. This is C0, this is C1, this is C2. Okay. So if somebody asks you, okay, if somebody asks you, okay, let me describe something else first. Okay, let me describe Dunn index first. Okay, this is easier to understand. So if these are the 3 clusters that are given to you, can you say that, I mean, from the ideal properties of clustering, these clusters should be far apart and individually they should be compact?
Yes.
Okay. So if I want to look at the overall clustering, okay, can I make it like this? Can you find the largest inter-cluster distance? Intra-cluster distance, rather, I should put it like this. So when I'm saying that, look at the largest within distance. So if you think about this cluster 2, this would be the distance, right? Yes or no?
Yes.
If you look at maybe say C1, I believe that maybe this looks the highest. Yes or no? And if you look at maybe say C0, this appears to be the highest.
Yes.
So out of these 3 distances, which is the highest for C0, right?
Yes.
Okay. So let's say this value is A, or maybe say this. Let's call it say Z. Okay. Let's say this value is Z. Can you find also the smallest across distance? Can you find this?
We can.
And if I try to ask you what is the ratio for them, okay? So compute the ratio. Let's say this is say P, okay? And now you try to find out the ratio P by Z. What can you say about it? Should it be higher the better or lower the better?
Across the distance, right? It should be higher.
No, think about this. This is the formula for this. This is P by Z. So if you want this ratio to be higher, you want P to be higher, right?
Yes.
Okay. So is it acceptable? You are saying that you are looking at the smallest ratio, right? Smallest across ratio. So we want P to be high, right? But we are still looking at the minimum of that. Yes or no? Think. See, typically what we want across distance to be high and we want this to be low. Does that make sense? We want within to be low and across to be high, right? Okay. The only thing I'm doing is I'm picking up the smallest across distance. Yes or no?
Yes.
Okay. So when you pick the smallest across distance, what would be the smallest across distance?
Smallest could be C0. So
You have to see, okay, smallest across distance, what it would be. Okay, so let me define, okay, this is actually defined for every cluster. Okay, this is defined for every cluster. So this is not defined for every point, it is defined for every cluster. So first you try to find out the smallest across distance. Okay. First you try to find out the smallest across distance. So for which cluster do you want me to do it? First, let's see this. For which cluster do you want me to do this?
C naught.
Okay, let's do it for C naught. Okay, let's do it value for C naught. Okay. Let's try to find the smallest across distance. Okay. So you do not have to count C naught. Okay, you do not have to count C naught. So what are the two other clusters possible? C1 and C2, right? Yes or no? Okay. So this is done with respect to, so the numerator comes with respect to other clusters. So in your other clusters C1 and C2, which is the smallest across distance? It will be this one, right? Correct me if I'm wrong. It will be probably this one. Yes or no? I have to find the smallest across distance. Does that make sense?
Yeah.
Okay. And if you look at the largest intra-cluster distance, what would be this?
Largest would be the last point.
So when you are doing this largest intra-cluster distance, that is coming from C naught. That is coming from C naught. So the largest inter-cluster distance would be this. So if this value is P and if this value is Z, now we have to decide, okay, if P by Z should be high or low. Think about this. For a good clustering, P by Z should be high or low. In the ideal case, what can you comment about Z? It should be as low as possible, right?
Yeah.
It should be as small as possible. Okay, so if it is low, what it will do to the ratio? It will make it high. Yes or no? So
Yes.
higher the better.
Yes.
But now think about P. Okay. So if you think about P, so this is the what we say is it's the smallest across distance. We also want this to be high.
Yes.
So can I say both values are contributing towards a better metric if if P is high and Z is low? See, if P is high, the metric becomes better, right? If Z is low, then metric becomes better. So essentially, both of them, if Z is low, the ratio becomes better. If P is high, ratio becomes better. So can I say higher the better overall?
Yeah.
Both contribute to the same thing, right? So this is higher the better. This is higher the better. So if you can do it for this cluster 0, can you do it for other clusters also?
Yes.
Can you do it for C1? Can you do it for C2? Okay. And if I average it out across the clusters, I will have the overall done index. Does that make sense? I will have the overall done index. Does this make sense? Okay. So this is your done index. Let's do one more. This is called as Kalinski-Harabash. See, most of the metrics that you are going to see today, they have a formula in terms of, within and across only. But ultimately, you have to decide, okay, whether higher the better or lower the better. Okay. Let's say this is the scenario. These are some of the clusters. This is C0. Maybe say this is C1. Okay, this is C2. Okay. Okay. So Kalinski-Harabash, what it does is it computes separation by cohesion. So separation, as you know, is measured by across, and cohesion is measured by within. Okay. Now let's see, okay, how to measure it. So I'm going to show you what separation is. So can you figure out the individual centroids? Can we figure out the individual centroids? We can, right?
Yeah.
Okay, so let's say this is the individual centroids. Can we figure out the global centroid also? This would be, say, the global centroid. Does this make sense?
Yeah.
Okay. So using the global centroid, how do we measure separation? Think about it. Using the global centroid, how do we measure separation? Can I say I can count this distance?
Yes. If the
Count this distance, and I can count this distance.
Yeah.
D1 plus D2 plus D3. What do you want this distance to be, high or low? This is separation.
High.
High, right? Okay, so this is your separation with respect to the global centroid. And cohesion is, can you do it for each individual cluster?
Yes.
Okay. Can you do it for each individual cluster? So, okay. So if you divide this, you want higher or lower value? You want higher or lower value? Think about it.
What's your question, Santi?
If it is higher the better or lower the better?
The cohesion.
See, cohesion is lower the better or higher the better?
Lower the better.
Lower the better, right? So if this value is low, Kalinsky-Horabaz will become bigger, right? This is the ratio, right? If cohesion is low, this will become better. For ideal clustering, cohesion should be low, right?
Yes.
And what about separation? Separation is also, I want it to be high for an ideal case, right? So higher, right? So can you say it typically is higher the better?
Yeah.
Okay. So this is one more metric that you can use. Okay, Kalinsky-Horabaz index. There is one more which is called as this Davies-Bouldin index. By the way, I forgot to mention that Dunn index is not preferred that much. Okay, Dunn index is not preferred that much. You may not find the implementation of this, okay, in your Python. But for others, you may. So if you want to implement Dunn, we can do that as well. But it is not preferred that much. Silhouette score and Kalinsky-Horabaz, they are the ones which are used the most. Even this one is also used quite fairly. Davies-Bouldin index. Okay. So this is given as like this. So this is cluster 0, this is cluster 1, this is cluster 2. So you are going to do it per cluster. Okay, so for which cluster do you want me to illustrate this?
C1.
Okay, let's do it for C1. So let's find Davies-Bouldin index for C1. So the formula is this SI plus SJ divided by DIJ. Okay. So let's call it, so what is SI? So SI is the within distance of cluster C1. So we are doing it, let's say, for cluster I. Okay. Since you said you want to do it for C1, I is 1, right? Yes or no?
Yes.
Okay. So we want to do it for within distance for C1. Okay. So if you do this for C1, again, there are many ways to compute this. You can, so if there are 4 samples, you can do 4 choose 2.
Yes.
Okay. And you can take the average of that. So that would be, so this is the average within distance. Okay. So this is for C1, for which cluster you want doing this. Okay. This is one way to do it. You can take with respect to centroids also and then do this. Okay. So if you do it for all possible values, that would be 4 choose 2, 6 combinations.
Yes.
If you do it with respect to centroids, that will be 4 combinations. Okay. So you can take the average, but however you want. Okay. Both are acceptable. Now,
that
Yes.
won't make much difference. Like if you do 4-2 or like based on the centroid.
Let's say all possible pairs. No, it will not have much difference. It will not have much difference. Because the way you will be computing SJ, okay, will be the same then. You cannot have different ways to compute it. See, you will get different values if you use these two different metrics, but the idea will not change. Higher the better or lower the better.
Okay.
Okay, idea will not change. Let me see what is the exact way to do it. I mean, just to confirm this. It's with respect to centroid only. This is preferred. It's with respect to the centroid. It's with respect to the centroid. Does that make sense?
Yes.
It's the average distance that you're having. Okay. With respect to the centroid. Okay. Now, which is the closest cluster to C1?
Closest cluster could be C0.
Okay, let's assume that okay, it is C2. Okay, let's assume the closest cluster is C2. Let's assume the closest cluster is C2. So just to avoid any ambiguity.
Okay.
Okay, so I'm just saying, okay, assume that the closest cluster is C2. So can you do the same for this cluster 2 as well? Go to the centroid and compute these distances.
Yes.
So this is your SJ. Okay, average within distance for C2, which is the closest cluster. Okay, nearest cluster. Does this make sense? Okay. And Dij is the distance between cluster 1 and cluster 2, which is the closest cluster, which is the distance between the centroids. Which is the distance between the centroids. This is the distance between the centroids. Okay, this is Dij. Okay. Now let's see. Okay. Do you want Dij to be high or low? Do you want Dij to be high or low?
Dij should be high.
High, right? So if I make it high, Daly's Borden index goes down, right?
Yeah.
So lower the better.
Lower the better.
Okay. But think about SI and SJ now. Do you want them?
Below.
It's within distance. I want them to be low, right?
Oh, yeah.
If both values are low, then I have an ideal clustering, right? SI and SJ. SI, SJ low, better is the clustering. Dij high, better is the clustering. So overall, lower the better, right?
Yes.
Both values contribute to the same thing. So this is the only metric that you have seen, which is lower the better. All others are higher the better. Does that make sense?
Yes.
Okay, so these are the four metrics that we have discussed. So we'll see implementation of Davies building, Kalinske, Harabas, and silhouette as well. Okay, and the silhouette as well. Okay. All right, so let's implement them one by one. Before we do that, any questions? Anyone with any questions? Yes, people, any questions as such?
No, from my side.
Okay, just give me a second. I'll just transfer this file. Okay, I'll do this after the class. Okay, this iPad is, I think, out of storage, so I'll do it after the class. I'll switch to the other device. Can you confirm if you're able to see the screen?
Yeah, we can.
Okay, all right. So let's start implementing these algorithms one by one. Okay, let's start. I'll just give it a name. Let's import pandas and NumPy. I'll import okay, Matplotlib as well. Okay, let me make a small data set quickly so everyone can visualize this. You can make a classification on a regression data set, it will not matter. I just need to use the features. I'm not going to use the outputs. Okay. So let's say some number of samples, say 100. I want two features so I can plot it. I don't care about the classes, okay, because I need X only. Okay, let's just do this. I want both the features to be informative, none of them to be redundant. Okay. So I only need X, okay, I don't need Y. Okay, let's plot this. So I'm plotting this data, the two features. So this is how the data looks like. Let's give it some access names. Let's say access X1, X2. Okay, and let's call this as say original data. Okay. Let me write PLT.show as well. Okay. Now, how many clusters do you see? We'll be implementing k-means on it. How many clusters do you see? Or you tell me the number of clusters, I'll show you what will k-means obtain. How many clusters do you want to figure out?
5.
Okay, let's go with 5 clusters. Okay, so 5 is the number of clusters that we are going with. Okay. So let's fix this value. Okay. Okay, so I'm going to, so any clustering algorithm, right? It's present in the library sklearn.cluster. Okay, any clustering algorithm is present here. And we're going to implement this k-means. Okay, so let's call this k-means as say km. Okay, you have to provide the number of clusters to it. So I'm saying that the number of clusters is 5, so which is k. And okay, and now I'm going to fit. So since there are no outputs, I will be fitting onto my X only. Okay, so I fit it onto this data. And now, what is the output of any clustering algorithm? What is the output of any clustering algorithm? Cluster labels, right?
Yeah.
And how many outputs will be there?
5.
100.
Sorry.
For each sample, there will be an output starting from either 0 or 1 or 2 or 3 or 4. Okay. So if you look at, so these are called as labels, cluster labels. So these are your cluster labels. Or you can also call it cluster memberships. You can also call it cluster memberships. Okay. So from these labels, can we determine how many samples are in cluster 0, how many are in cluster 1, cluster 2, cluster 3, cluster 4? It's easy to do, right? Yes or no?
Yeah.
So you just need to count how many zeros are there, ones are there, twos are there, and so on. Okay. So you can use collections, counter from it, or you can use this NumPy unique. Okay, and return this. So it tells you in cluster 0 there are 18 samples, 1 you have 25, 2 you have 22, 3, 19, 4, 16. Okay. Let's plot this. Let's plot the clusters to see how good k-means is doing. Okay. So let's do this. So color will be equal to this labels that you got. So these are your 5 clusters. I'll just label it as well. I mean, give the legend. So labels will be the unique values in the clusters. You can give it, say, like this. Okay, you don't have to do it like this. You can simply say how many clusters you identified, right? And you can say range of, so list of range of 4, list of range of k. These will be the number of clusters, right? So this range of k will give you what values? What is k?
The number of clusters.
5. So range of k will give you what values? 0, 1, 2, 3, 4.
Yes.
So you're converting it to a list. Otherwise, it will return a range object. Okay. Okay. See this. So it tells you, okay, these purples are these zeros. 4s are the yellows. 3s are these greens, light greens. Okay. 2s are the light blues. This is slightly dark blue. Okay. So these are the clusters that you have. Okay. So this is for 5. Anything else that maybe say I want to show you the cluster centers. So let's say you want the cluster centroids. So you can print the cluster centroids or cluster centers like this. So these are your cluster centers. I'm going to plot it so that you all can see. Okay. I'm going to plot it on the data itself. I'm going to show everything in red color. Okay. So I'll just do it like this. So say for J in these cluster centers. Okay. I'm going to say, okay, give me plt.scatter. I want to plot J of 0 and J of 1. Okay. Which will be the 0th axis, first axis. I'll say the marker is maybe say the star. So you will see a star there. And the size to be, say, 25. Okay, so you can see, and color maybe say red. Do you see these 5 centroids?
Yes.
Maybe I'll just increase the color. These are 50. I mean the size. Okay, I hope you can see it now. So these are the cluster centroids for each of the clusters. Okay, I'm going to give you a query point, and you tell me, okay, what will be the prediction? Okay. So let's say this is some query point. The query point is this plt.scatter. Okay. Let's say the point is maybe say 1, minus 2. Okay, and I'm going to put it in let's say with a special symbol, let's say this cap. Now you'll see it as a triangle. Okay, and I'll say size is maybe say 80. So you can see it clearly. It would be a triangle. Okay, okay, this is fine. Let's see which color it comes out to be. Okay, do you see this? This is a triangle. So what would you assign it as? If this is a query point, what would you assign it as? So if somebody asks you to which cluster it should belong to, what would you say? This triangle.
This triangle will belong to the cluster 3.
To the green cluster, right?
Yeah.
Cluster
Yeah.
3. So I'll show you that. Okay, the value is 1, minus 2. Okay. So you can use this model Km to predict as well. So pass this value, which is this 1, minus 1, 2. What was the value? 1, minus 2. Okay. And what it should predict? 3. Make sense?
Yes.
Okay. So this way you can visualize, okay? This way you can visualize what is happening. Okay, let me just say prediction for a query point. Okay. I'm just going to give it, okay, plotting centroids. Clusters, okay. Plotting clusters, okay. All right. Okay, all right. So this is how you predict. Any questions about k-means? Shall we do the elbow curve?
Yeah.
Find optimal number of clusters. Okay. So see, there is a property in this, okay, which is called as inertia. This is computing the within distance, by the way. So this is the within distance for the 5 clusters that you obtained. Okay, so this is the within distance for the 5 clusters that you obtained. Please note this. I advise you to do normalization before you run this. Okay, I missed that because my data is kind of. Do you see that my data is between say -3 to 3? Yes or no on the x2 axis?
Yeah.
Okay, I think I didn't use y label. Okay. So similarly on this side also it is between -3 to 3. So it's already kind of standardized. So that's why I didn't do it. So I'll just make a note here for you. Okay. Standardize your data because it's a you can say standardize or normalize your data. Prefer normalization. So I will just write it like this. Okay. Normalize your data before you apply. Yeah, I'll just make it a heading. Let's say note. Okay. All right. So I'm going to run a simple for loop, and then we will plot the elbow curve. So let's say for k in. So in what range shall we go? From 2 onwards to up to how much? We have 100 samples. I can go up to 100 also. Do you want me to go up to 100?
Okay.
Need to go that far, but I'll show you. Okay, just in case you want to go up to 100. Okay. So let's say your algorithm is k-means. I'll cut here. Shall we normalize the data here? What do you recommend? I'll normalize it so that you can keep track of it. Okay, pre-processing. So normalize my data, applying the clustering algorithms on it, and then I'm simply collecting the inertias, the within distance, okay, for different Ks. So just append the inertias. Okay. And this is all your inertias, by the way. There's a problem. SQL on pre-processing.
Pre-processing.
Yeah, spelling mistake there. Normalized it. Okay, it's computing your inertias. Let's see. It's computed all your inertias. Do you see that? What is the last value?
0.
So within distance for all the samples would be what? 0, right? So I'm going to plot these inertias. So let's give it a title, say plotting elbow curve or the knee curve to determine optimal number of clusters. So you can do PLT dot plot. So you have this range of 2 to 100 here. And this is your inertias. So this is what it comes out to be. I'll just make a note here. 1 second. So let me say PLT dot show. I'll just give some titles as well. You got X label, so number of clusters. Okay. Okay, and let's say this is the title is the elbow curve. Right. So just by looking at it, it's difficult to identify the elbow, right? And this is where the elbow must lie, somewhere here.
Yes.
Okay, but so I'm going to do it in a small range. Okay, I'm going to do it in a small range. Okay. So that you can clearly see there would be an elbow. I'm going to do it between say 2 and say 20.
20.
Okay. So inertias of up to 20. So 2 and 21 will be how much? 20 minus 2 plus 1, 90. Okay. Now, what value do you see looks nice to you? Closer to 12. Yes or no?
Yes.
Okay, so I'll plot the value for 12 so that you can see. So PLT dot scatter, we have all confirmed that okay, looks for 12 and inertias. So inertia value would be, so the first value is for 2. So inertia is 0, right? The 0th value is for 2. So 12th value would be for how much? 10 or 10, right? Okay. So 0 means 2, 1 means 3, 2 means 4. So 10 will mean 12. Okay, this is all right. Inertias. Do you see this? So I'll give it a special marker. Maybe say triangle. Okay, and maybe I'll increase the size 50. Okay, and color say red. Okay. So this is the best value that you have corresponding to your elbow point. Okay. So this is the elbow. This is the elbow point. Any questions? ESP, any questions?
So you have taken 12, that is the point, and the inertia you have given 10, right?
So because the first inertia value is for cluster 0, right? 2 clusters. See, look at these inertia values that I collected. What was the first number of clusters for which the inertia is computed? 2, right?
Yes.
So so inertias is a list, right? That I computed this. So the first value is computed for how many clusters? The within distance, this first within distance is computed for how many clusters? See this.
2. Okay.
Okay, so I want to do it for 12 clusters. Yes or no? 12 I know is the best value, right?
Yes, yes.
So for 12, what value should I plot? The 10th value, right? Because this first value is for 2, this is for 3, this is for 4, this is for 5, this is for 6. Can you simply count? If the first value is for 2, 10th value will be for 12th, right? Yes, Nisha, why is it so hard to understand? I don't get it. See, this is the within distance sum for what value?
Second cluster.
Not second cluster, for 2 clusters.
Okay, for 2 clusters. Okay,
Okay, so this is the within distance sum for what value?
for 3 clusters.
Okay, so when you go, if you have identified from this curve that
The elbow point. Okay.
the elbow point, that for 12 you get the best results, right?
Yes.
So I would be plotting it for 12 comma that inertia value, right? So where is this inertia value located? It's there in my list of inertias. So what is the value corresponding to 12 clusters? At the 10th location of inertia, right?
Like, I'm
You
like,
lost.
I can understand that 12 bit somehow that inertia 10. I don't know like why I'm losing.
Okay. Think about this. Do I have the plot for say 0 number of clusters? Does it make sense to plot for 0 number of clusters? No, right?
No.
Does it make sense to plot for 1?
No.
It
Okay.
makes sense only to do it for 2, right?
Yes.
Okay, so here, when the number of clusters are 12, what is the inertia value?
10.
No, don't forget, don't say 10 because you have seen it. Can you run it one more time and figure out what is the inertia value? Okay, let's see this. I'll just run it for 10. Okay, you see this. So now I'm fixing the number of clusters as 12. Okay, does that make sense? Okay, yes or no? And this would be the inertia value. Does this make sense or not?
0.5.
Okay, so this is the value that I have plotted, 12 comma this value. Forget everything else. This would be here.
Okay.
12 comma this value has been plotted here. Okay, I have stored it in the list of my inertias. Okay, and in this inertias list, it was at 10th place. It was at the 10th index.
Oh, okay. From that, simply was like in that second cluster, third cluster, on the 10th cluster's value that you're plotting. For this, it took me this long.
That is corresponding to the 12 clusters. Sir. Anything else about this k-means? Is it clear? Shall I go to the next algorithm? Any specific questions about this? Shall I show you how to compute the different evaluation metrics? So let's go to the first silhouette samples. एक सेकंड भैया Okay, so let's start with silhouette samples. So this will give you the results for you can say all the samples, all the 100 samples. So what you have to give it is the model that you have, which is KM. Okay, so for what number of clusters do you want to compute this? Tell me this. Shall I do it for 12?
Okay.
Okay, so this is just to show you for 12. Okay, so so please note that this is run for 12 clusters. Okay, so you have to give it your data, which is normalized X. Okay, I'm not very sure. Do I have to give it labels or? I think I need to just give the data and the labels. It should be able to compute silhouette samples. Just a second, please. I mean, if it is asking for the model, then I don't need to give the labels explicitly. Yeah, X and the labels. Okay, so I shouldn't give the models. Okay, so just give the data and the labels. Okay, what's the problem? Spelling mistake is that silhouette samples. So do you see 100 silhouette sample scores? So for some of them it is negative, they have not been clustered well. For some of them it's a 0. So they have not been clustered well. For so values which are greater than 0.6, 0.7, those samples have been clustered well. Okay. So the mean of this is going to be called as silhouette score. Okay. The average of all of them is going to be called as silhouette score. So you can use this. By the way, there is a function for it as well. So you can say sklearn.metrics, and you can compute silhouette score. Okay. Compute the silhouette score. Okay. And this will be the same value that I'm computing here. Okay. So you just need to pass this. It will compute the same thing, the average of the silhouette samples. Okay. Silhouette. Do you see that is the same value?
Yes.
So it is present as a separate function also. So if you just need the silhouette score, the overall clustering goodness score, use this. Okay. Otherwise, you use that. Okay. So this is, I'll just make a note here. These are your evaluation metrics. Yeah. Score, also called as silhouette coefficient. Okay. Let's do the second one. This is say Davies-Bouldin. Okay, and the third one would be your Kalinske-Harabash. BAM index is not there. And it's not very popular either. Okay. Okay, let's do Davies-Bouldin. Any question from anyone? Index. So this is your Davies-Bouldin index. Just a second. Okay, let me just check. Is it called as Davies-Bouldin score or Davies-Bouldin index? Sometimes they change their names. Okay. So, as Davies-Bouldin score. Actually, in R, it's called as index. There are many. I mean, I use a lot of metrics across different libraries. So sometimes I even get confused. This is Kalinske-Harabash. Again, I'm not sure it is index or what. I think it must be score only here. Okay, yeah. So this is the Kalinske-Harabash score. Okay. So using silhouette score also, you can actually predict what is the optimal number of clusters. So let's do that. So I'll just the same code for finding the optimal number of clusters using silhouette score. You can run it for the others as well. Okay. So let's compute the silhouette scores. Let's call it SS. Okay. And then I'm going to append the silhouette scores. So I need to give the data, normalize X, and the labels. Okay. So these are your silhouette scores. I should have run it for the whole thing. Okay, maybe I'll stop it. Okay, otherwise it'll take time. Okay, just a second. I'll run it for up to say 20. Okay. And then I'll plot this for 20. So silhouette score is between -1 to 1. So higher the better. Okay, let's see for silhouette scores. Yeah. And this is the silhouette scores. So this will plot after looking at the curve. Okay. Let's see. So what do you think the maximum value is? Close to 7, right? It hits at 7. Yes or no? Okay. So higher the better, right? So it hits at 7. So you can just plot this. So silhouette score is telling you that 7 number of clusters are the best. Okay. So this would be at inertia as 5. So sorry, this would be at SS of 5. Sorry, this is 1 second. So it's not 7 then. I think it's after this 8. It's 8. Okay, so this is the value, which is the highest. See, please note that there is no way to validate it because it's unsupervised. So you need to reach out to a domain expert who can actually tell you what is a good number of clusters. But this is what you achieve using the silhouette score metric. Okay. You can try Kalinske, Harabaz, and other things, and then see. Okay, and then see. Okay. Anything else about k-means? Yes. Anything else about k-means? We'll implement the remaining ones tomorrow. Not now. We are almost up on time. It will take me some time to discuss dbScan and agglomerator. Okay, we'll do that tomorrow. So, any other questions? Yes, people. Any other questions?
No, sir.
Okay, so let's meet tomorrow. I'll share this and the handwritten notes in a few minutes. Okay, on your drive folder. So, bye everyone. Have a good day. Bye.
Yeah, you do the same. Bye.
Thank you.
Bye everyone.